Hello, I am Mo Kiali, and I'm very excited to tell you about the research I have been doing here at the University of Washington over the past year. This work, which we're calling Causal Relational Learning, is all about integrating the knowledge of domain experts with big data to unlock insights previously not possible. First of all, though, a word of thank you to my mentors here at UW, Dan and Babak. Without their help, not only would this project have been impossible, but I would not have entered the world of research in the first place. Further, thank you to my collaborators from Duke University and UC Santa Barbara for your valuable contributions. The core idea I want to convince you of today is that big data is not enough. While our unprecedented ability to collect troves of information from transactions, sensor networks, and social networks has allowed us great insight, this same data has given us a false sense of certainty. Or, as my mentor Babak put it, over-reliance on data is just as bad as ignoring data. Let's explore this with an example. Imagine we wanted to answer the question, does smoking cause lung cancer? We undertake a massive data collection effort, here already done for us by the CDC and others, and we find a clear pattern. Over the past 100 years or so, a drastic increase in smoking, reaching a peak in the mid-1950s, followed by an equally large increase in the number of lung cancer deaths, with about a 40-year delay between the two. It seems the conclusion is clear. Smoking causes cancer. Case closed, right? Not quite, actually. Because, considering the relationship between the flu and the flu vaccine, we actually find the same trend. Looking at the data the CDC published last year, during last year's flu season, we find a drastic increase in the number of flu vaccinations in October, followed by a peak in flu infections 4 months later. If data in this pattern was enough for us to conclude that smoking causes cancer, should we not then conclude that the flu vaccine causes the flu? That would be a flawed conclusion, of course. So, where did we go wrong? Was it that we needed more data or better data? No, because neither of those changes would have altered the trend we see. The problem is that we did not use what you might call common sense, or what I will call domain expert insight. If we want to have any hope of building algorithms that help us make informed decisions, we need to find a way of communicating to our computer systems not only data, but also the insights of domain experts. So how can we inject this understanding of common sense into our systems? One solution, discovered in the 1920s by geneticist Sewall Wright and expanded on greatly by Judea Pearl in the 1980s, is called the causal diagram. This line of work has found tremendous success in epidemiology, public policy, and economics. The core idea is communicating cause and effect relationships using ball and arrow diagrams. In the flu scenario, we encode our knowledge that changing of the season causes an increase in the flu. And this change simultaneously influences the CDC to ramp up vaccination efforts. You can see this in the arrows in the diagram on the left side. Now pay attention to how there are two paths from vaccination to flu. There's the direct path, the obvious one, but there is also a path via the CDC and season nodes. So it becomes clear that there's a variable that must be adjusted for, the season, which we technically call a confounder, and without this change, any analysis would be misleading. Meanwhile, if we look on the right, there is no confounder that explains away the effect of smoking on cancer, which is why today we believe in a causal link between smoking and cancer. However, causal diagrams do have some limitations. Consider what kind of causal diagram you could draw to encode the assumption that vaccination has a community effect. That is, that the vaccination of one person reduces the odds that another person within the same community gets sick? Or, how would you communicate that the causal effect exists, but only under some conditions? For example, if we want to say that remote communication skills are important for cross-university collaborations, how can we limit those causal links to specific scenarios? This is where our work comes in. My contribution to our research was the creation of a language, which we affectionately call CARL, for Causal Relational Language, which allows for the creation of causal diagrams in situations not amenable to traditional causal diagrams. In the first line, you see the assumption that if A and B are friends, and B is vaccinated, then that affects the odds that A gets sick. Separately, the second line lets us express that paper P's odds of success are causally affected by the remote communication skills of its authors, say, how good they are at using Zoom, only if those authors belong to different institutions. In short, this language allows us to communicate domain expert insight in ways previously difficult. Now, what our framework then does with the language is combine it with a concrete database instance to produce what we call a grounded causal model. So in this case, the high-level rule that friends' vaccinations affect community health is combined with the database relation that says Alice and Carlos are friends, and so the rule gets translated to the diagram at the bottom, where Alice and Carlos affect each other, but Bob does not. In our research, we deployed CARL against a number of datasets to test how well it performed in answering tricky causal questions. In the interest of brevity, I will highlight one experiment I performed on a dataset called the Nationwide Inpatient Sample. This is a dataset of 7 million hospital admissions during the year 2006. After encoding my assumptions, I asked the system to estimate the effect of hospital size on the affordability of care. I had analyzed the data in a more naive fashion first, without CARL, and found that larger hospitals were much less affordable, a little under 40% more expensive. However, CARL returned the opposite conclusion, namely that large hospitals were on average 10% more affordable. What had happened is that CARL realized that the severity of illness and the nature of procedures being performed at large hospitals was very different from those being performed at small hospitals, and therefore it adjusted for a sufficient set of variables that would make the comparison fair. We believe CARL's results to be more correct, as several studies have shown that economies of scale do exist in the medical sector, and, in fact, it is the policy of several national governments to consolidate smaller hospitals to increase productivity. If you want to learn more about our work, you can take a look at our main paper, Causal Relational Learning, to be presented at SIGMOD 2020, which showcases the language and all the theory needed behind the scenes to make it work, as well as 3 experiments on real-life datasets from the medical and academic publishing industries. We are also submitting a demonstration paper to VLDB 2020 to showcase the full polished system in an interactive setting, which we are currently in the process of implementing. Finally, we are releasing our work as open source code on GitHub in the hope of making it as widely useful as possible. Of course, GitHub has the advantage of being the original all-online venue. I hope I have given you a flavor of why causal inference is an important and rapidly developing field, as well as what kind of exciting work there is left to do. That's all I have for today.